Hi guys, going to give a quick run through on the use of a current clamp meter. Obviously, when you're purchasing one of these, make sure that you're buying one that has the correct settings, whether that's AC or DC voltage or amps and milliamps. When we're utilising the amps and milliamps for the current clamp side, make sure it also measures AC and DC. Obviously, with the changes that have happened in relation to selection of RCDs, it's vitally important that when we are having a look at measuring installations, particularly for periodic inspections, it's vital that we measure these DC components that might be getting inserted back into our RCD's toroidal core. Okay, so when we're carrying out these measurements, there's two ways in which we can carry out these current measurements. It's either direct measurement, where we're clamping the cable and measuring directly the magnetic field on the cable for the current that's flowing through it, or we use that differential measurement where we are looking at the imbalance between the two magnetic fields as the current's flowing forwards and backwards around these cables. Yeah, if there's any current flowing down to earth, then the current clamp would be able to detect that and the difference in the two magnetic fields. Okay. As well as that, we need to make sure that we're measuring AC or DC, depending on what it is that we're looking for. So either that alternating current for your leakage or your DC setting to work out what the DC components are flowing back into your RCDs. Okay. So direct measurement, when would we normally use direct measurement? Well, generally, health and safety. For yourself, when you're carrying out inspection and testing, remember you might be disconnecting these big green and yellow wires in your installation. So we're looking for divergent neutral conductor currents, these circulating protective conductor currents that might be flowing through your earthing and bonding arrangements. Okay, so obviously we carry out those measurements before we isolate the installation, and then carry out the measurements again to make sure that these currents have disappeared. Remember, if you're still measuring currents at the point after you've isolated the system, then you should not be disconnecting anything. You should be contacting the DNO. Other ways in which we can utilise this direct measurement again is for leakage current. Generally, it's only really ideal for when we're working on a circuit where there's no parallel paths. Yeah, so there's no current circulating elsewhere within the system. For the purposes of the test moving forward, we're going to be looking at the differential method. Okay, can be used for system or circuit IR, insulation resistance earth faults, but generally we're going to be looking at system or circuit AC leakage, or the DC components that are getting inserted back into the RCD's toroidal core because of the electronic components that we've got connected downstream of the RCD. Okay, so important information we need before we start. Should be looking at your RCDs. You'll see here we've got a dual load RCD, split load RCD, dual RCD board. We've got an 80 amp, 30 milliamp RCD, but you'll see both of them, again, same ratings, both of them are type A RCDs. Okay, so this information is important. Why? Well, when we look at the different types of RCDs, type AC RCDs, we should be using them only in installations where we have purely resistive loads. Okay, whereas now the general use RCD that we should be using is a type A RCD that allows up to 6 milliamps getting inserted back in through the toroidal core. If we used a type AC and we had these electronic components connected, type AC RCD, and we had these electronic components connected that are dumping the DC components back into the RCD, we would have reduced or extended tripping times. Okay, if we had a type AC RCD in front of these circuits. Type F, might use type F where we have, for example, variable frequency drives. They can handle up to 10 milliamps. On the DC components getting inserted back into the RCD, or we might use type B. They can handle more than 10 milliamps. But irrespective of the RCD type, obviously the information we've just looked at is about the DC measurements. We need to be aware that each RCD, we're dealing with a maximum leakage of 30% of its trip rating. So if that's a 30 milliamp RCD, that we've got here for the type A, then that would be 9 milliamps max leakage. All right. So how do we carry out this test? Well, we carry out this test under normal load conditions with all the circuit breakers and the RCDs in the on position. We're wanting to see how this installation is actually performing. And it's pretty straightforward, the tests. We just current clamp the incoming supply cables. Either that will be at the top of the main switch or maybe before it goes into the local isolator from the DNO, if there is one there. And we take a note of the AC leakage current. Then we test each RCD, checking the AC leakage and the DC components flowing back through that residual current device. Okay, so we check each one of these RCDs, taking a note of AC and DC currents. All right, and then you would then test each individual circuit. Again, AC leakage definitely, but you might also check the DC components if, when you were back at this stage, you identified that the DC component here was more than what the device is rated for. Okay, so taking a note of these values as you test through the circuits. Okay. So once you've got all those values, you'll see there the total leakage that we got at the start. We got 20 milliamps. Obviously, we've only got 2 RCDs. We're expecting a maximum of 18 milliamps combined between those 2 residual current devices. So we're going to have to investigate this non-compliance. Looking at RCD1, the AC leakage on that RCD was 11 milliamps. So we're going to need to carry out further investigation on that side of the board. The DC component was 4 milliamps, so that's less than the 6 milliamps that were allowed for that type A RCD, so we're quite happy with that, so we don't need to investigate the DC components. So if we look at the leakage values that we obtained, you'll see we have 2 circuits here, circuit 2 and circuit 4, where we have higher leakage. Okay, so we would investigate those circuits, switching items of equipment off, unplugging them, and identifying what's happening to the circuit as we are running through that investigatory stage. Okay, where we have items of equipment that have higher leakage, then we might then be looking to, rather than having just the 2 RCDs that we've got on that board, we might then look to put a third RCD, so we might have to put a separate enclosure in there with another supply coming in, to then further subdivide the installation, so bringing that overall leakage down. Okay. When we look at RCD2, you'll see there we've got 9 milliamps. Okay, so 9 milliamps on the AC leakage, type AC, that's perfectly fine. However, it is quite high. It's on that cusp of not complying. Okay, so when we're looking at the AC leakage for the rest of the circuits, you'll see there we have 7 milliamps on circuit number 7. So if we have 7 milliamps in circuit number 7, we're definitely going to investigate that circuit and find out what's going on. Again, possibly subdividing the installation more. All right. But looking at the DC components through that second RCD, you'll see there we've got 8 milliamps. Now remember, the maximum leakage that we can have for this type A RCD is 6 milliamps, so we have to investigate this non-compliance. So we're then having a look at all of the DC components going back through each one of those RCDs, and sure enough, that circuit number 7 that we're already investigating anyway, what have we identified? We've identified that we've got 6.5 milliamps here. So hopefully once we identify what's going on here, with the higher leakage, and if we further subdivide the installation, through that investigation, we'll hopefully bring that 8 milliamps down below the 6 milliamps, ensuring that when the RCD operates, it's going to operate within the the time frame required. Remember, these RCDs are rated at 30 milliamps. They will be providing additional protection, so they should trip within 300 milliseconds if it's a BSEN 61009 or a BSEN 61008 RCBO slash 008 for the RCD. So it should trip within 300 milliseconds when it's tested at 1 times its trip rating. Okay, so again, remember folks, it's just a case of just unplugging items of equipment and identifying which items of equipment are actually giving you the higher readings. It's pushing these values up. Okay, so hopefully that's been of a bit of or a bit informative for you. So all I'll say, guys, is onwards and upwards, and I'll see you when you are back in the college.